So hello everyone, welcome to Positron Academy, and today's topic of discussion is on radiation quantities and units. So a unit is important for the measurement of any physical quantity. For example, if we consider any physical quantity like weight, like height, we do have a defined unit. For weight we have units in kilograms, for height we have units in meter, centimeter, and so on and so forth. Similarly, we do have a defined physical quantity and its corresponding units in the field of radiation physics, in dosimetry, and in radiation protection. So the ICRU, it reviews and it updates from time to time the concepts related to the quantities and units in radiation physics, in dosimetry, and radiation protection. And some of the quantity of interest to us in this presentation are activity, air Kerma, absorbed dose, equivalent dose, annual limit of intake, and derived air concentration, and we'll focus on these units in this presentation. So the first quantity which we try to understand is what we call as activity. So the activity of a radioisotope source is defined as its rate of decay and is given by the fundamental law of radioactive decay. And that is dN by dt for decay is equals to minus lambda times n, where lambda is what we call as decay constant and n is the number of radioactive nuclide present. Alright, so now coming back to the unit part. Activity has a unit of what we call as Curie, and it's named after the legendary Madame Curie. So 1 Curie is equals to 3.7 times 10 to the power 10 disintegration per second, and that's the activity of 1 gram of radium 226. But this Curie as a whole is a very big number, and in our day-to-day nuclear medicine labs we don't use activity in such high range. Rather, we use units in sub-multiples of this Curie, and these are millicurie, microcurie. So we use activities in this range, not as high as Curie. So although still widely used in literature, the Curie is destined to be replaced gradually by its SI equivalent called the Backwheel, and Backwheel is disintegration per second. So 1 Backwheel is equals to 1 disintegration per second. So the General Conference on Weights and Measurement adopted a resolution declaring that Backwheel, defined as 1 disintegration per second, has become the standard unit of activity, and 1 Backwheel is equals to 2.703 times 10 to the minus 11 Curie. And how this unit came, how this number comes over here. So we all know that 1 Curie equals to 3.7 times 10 to the power 10 Backwheel. So we can go and find 1 Backwheel, and it will be something value over 2.703 times 10 to the minus 11 Curie. And it should be emphasized that activity measures the source disintegration rate. It means activity tells you the rate at which the source is being decaying down, but it does not tell you anything about the emission rate of radiation produced in its decay. Activity has it does not tell you the rate of alpha, beta, gamma emission. Alright, so activity just tells you about the rate at which the source is disintegrating. So frequently, a given radiation will be emitted in only a fraction of all the decays. So a knowledge of the decay scheme of the particular isotope is important to infer a radiation emission rate from its activity. And if you want to know more about the decay schemes, how these alpha, beta, gamma radiations are being emitted from a nuclide, so I suggest you to go for my video lecture in my channel, which you will find as the name as radioactive decay and its application, where I explained about the decay profiles for alpha, beta, gamma. I also explained about the beta plus, beta minus, and electron capture. So those are being explained well in my presentation. So you can go and have a look on those part, how these radiations, radiations are being governed. So also the decay of a given radioisotope may lead to daughter product whose activity also contributes to the radiation yield from the source. And that's why in our definition of radioactive decay, that is dN by dt equal to minus lambda n, that is only for decay, because it's not the net disintegration, because at the same time there is some growth of daughter nuclide also. So for decay, that's the proper definition, that is dN by dt equal to minus lambda n for decay. we're not considering any growth. So for net decay, it will be something different. It's not the same as this one. So in now summary, we can now say that 1 Becquerel equal to 1 disintegration per second, 1 Curie equal to 3.7 times 10 to the power 10 Becquerel, and 1 millicurie will be 37 megabecquerel. I guess it will be more. You'll know how it came, how it actually arrives over here. So 1 millicurie will equal to 3.7 times 10 to the power 10 into 10 to the minus 3 becquerel, which you give it to 337 megabecquerel, and similarly for 1 curie it will be 37 gigabecquerel. So the specific activity of a radionuclide is its activity per unit mass of the pure material. So specific activity is equal to activity per unit mass of the pure material. So its old unit is in curie per gram and its new SI unit is in becquerel per kilogram. So to calculate the specific activity in becquerel per gram, we have to use the following formula. That is, specific activity is equals to Ng times lambda, where Ng is the number of atoms of the nuclide in 1 gram of the pure material, and lambda is what we call as decay constant, the rate at which the nuclide is decaying, and it is unit of second inverse. So now let's have an example of how to calculate the specific activity of uranium-235. The first calculate the number of uranium-235 atoms in 1 gram. So there are 235 grams of uranium in 1 mole. So in 1 gram we will be having this amount of moles of uranium. So this is the mole of uranium in 1 gram of uranium-235. And since there are this amount of atoms per mole, or Avogadro number of atoms per mole, so we'll multiply this result with our Avogadro number. So we'll get our Ng over here, which is this amount of atoms in per gram of the material. So next is, now we know specific activity is equals to Ng times lambda. We have the value of Ng, and lambda we can easily calculate from the formula lambda equal to 0.693 by T half. We know the half time of uranium-235 to convert it to seconds, and now we, after conversion of these in seconds, we get these lambda having value of 3.119 cross 10 to the minus 17 per second. So now put it in the formula, and finally we'll get our activity, our specific activity in becquerel per gram or curie per gram. So that's how we go and calculate specific activity. So the next topic of discussion is on absorbed dose. So according to ICRU report 85A, the absorbed dose is defined by D equal to D epsilon by dm, where D epsilon bar is the mean energy imparted to the matter of mass, and dm is a small element of mass, and the unit of absorbed dose is in joule per kilogram, or what we call as gray. So the effect of radiation does not depend on the energy transferred to the medium, but also on the energy absorbed by the medium. So that's the matter of mass m, and there's a radiation photons. So the effect of radiation does not depend on how much of the radiation are being imposed on the material, but rather how much radiation are being absorbed by them. So amount of energy absorbed per unit mass of the material is what we call as absorbed dose, and it has units in gray. So now let's try to understand some of the characteristics of absorbed dose. The first is energy imparted is the radiation energy absorbed in a volume. So now these are all the energy coming in the form of electrons or photons, and that's the matter having a volume V say. So the energy absorbed will be equal to the energy coming in, W in, minus energy going out, plus the interactions and the elementary particle process which happens over here. So these will lead to the effective energy absorbed by this material having volume V and mass m. So the energy coming in the form of electrons or photons, some of the energy goes out and some of the energy being created because of interactions of the radiations of with this matter having volume V and mass m. Alright, so the energy absorbed is equals to W in minus W out plus the amount of energy produced because of the interactions plus elementary particle processes like pair production, annihilation, nuclear reactions and radioactive decay. Next is that absorbed dose refers to an exactly defined volume and only to a volume V. So if I changed my volume, the absorbed dose will change. So for this volume, the absorbed dose will be different than this volume. So if I change my volume, my absorbed dose will change. And next is that absorbed dose, it refers to the material of the volume. So whether in the volume we have water or we have tissue and so on and so forth. So again, the absorbed dose, it refers to exactly a defined volume and only to a volume V, and absorbed dose refers to the material of the volume. So now let's try to understand through an example. So we have this amount of photons and that's the material of choice. There's the material over here and these are the photons which are coming, which are interacting with the matter. For at this point of time, it has interacted in a photoelectric fashion and these are the electrons or secondary electrons and like this. So now for absorbed dose, we have to define a volume and that's the volume V. Alright, so for this volume, the amount of dose deposited or absorbed dose will be because of these interaction for this one, for this one, for this one. So these three are the one which contributes to the radiation dose, not this one because it is outside the volume. So the energy imparted to the matter in a given volume is the sum of all energy deposits in the volume. So if the energy deposit in this one is d epsilon 1, d epsilon 2, d epsilon 3, d epsilon 4, so the absorbed dose is equals to the summation of d epsilon I from I equals to 1 to 4 by dm. So this will give you the absorbed dose for this interaction which happens in the matter having volume V and units will be in gray. So example, like we have radiation detector and a response to irradiation with a signal m in milliröntgen per hour, in microsievert per hour or whatever units you say. So what basically happened over there, so in that volume of air the energy has imparted, so this amount of energy is being deposited and summation of all the energy deposited will give you the energy imparted, which gives just to defined signal which quantifies the radiation is high or low, dose is high or low. If energy deposit is more, then definitely the signal will be high. So this signal, it depends on the energy deposit. If the energy deposit is high, then definitely the signal will be high and will get a higher reading in the radiation detector. So next is what we call as Kerma. So the field of indirectly ionizing radiation at any point in matter is given by the Kerma, the quantity Kerma. And is defined as the sum of the kinetic energy of all charged particles liberated by radiation in a matter of mass m. So we have a matter of mass m, these are all radiation coming over here. So it has coming over here and it knocked out an electron having initial kinetic energy of Ke1, this one knocked out electron having kinetic energy Ke2 and so on and so forth. So sum of all the kinetic energy in that matter of mass m will lead to the quantity called as Kerma. So it is defined as the sum of the kinetic energy of all charged particles liberated by radiation in a matter of mass m, and it has the unit of gray. And whenever the reference material is mentioned as air, we call as air Kerma. So next is what we call as exposure. Exposure is defined as the absolute value of total charge of the ions of single sign produced in air when all the secondary electrons liberated by photons in air of mass delta m are completely stopped in air, and the unit of exposure is in coulomb per kilogram, the amount of charge produced per kilogram of air, and the unit of exposure in use is Röntgen and is defined as the amount of X-ray or gamma ray which would liberate this amount of charge of either sign in 1 cc of air at standard temperature and pressure. So 1 Röntgen is equal to the is that amount of X-ray or gamma ray which will liberate 1 ESU of charge per cc of air at STP, and 1 Roentgen equals to 2.58 times 10 to the minus 4 coulomb per kilogram, and that's in air. Alright, that is for exposure. It has units in Roentgen. And as per definition, exposure is a quantity which is restricted to photons and to air as a medium. So for whenever you define exposure, it is for photons and medium is air. So next the topic of discussion is on what we call as equivalent dose. So the effect of radiation, it depends not only on the amount of energy absorbed, but also on the spatial distribution of ion pairs. So for example, if we have a tissue over here and you give 1 gray of radiation to it, so the effect of radiation does not depend not only on the amount of radiation given, but also on the amount of charged species, or the amount of the but also depends on the spatial distribution of ion pairs. If the spatial distribution of ion pair is very high, ion generation is very high, definitely the amount of response will be very high. So the effect of radiation depends not only on the amount of energy absorbed, but also on the spatial distribution of ion pairs. So biological effects of radiation will be different for different radiations for the same dose. For example, if I have a tissue over here and if I give 1 gray of alpha particles and if I give 1 gray of gamma rays, the response won't be similar. Response is different because of multiple reasons. One of the reason is that the alpha particles have higher LET, so the response rate will be pretty higher than that of the gamma ray. Eventually, both of them have equal dose. Both of them has 1 gray of absorbed dose, but still the response by the tissue is not similar. So biological effect caused by 1 gray of alpha particle is not equal to 1 gray of X-rays, and it depends on what we call as linear energy transferred. All right. So 1 gray of alpha particle, 1 gray of alpha dose is more effective than 1 gray of gamma dose. So hence in radiation protection, to account for this variability in the effectiveness of different types of radiation, we have to quantify a constant variable, what we call as radiation weighing factor, and is being used to multiply with the absorbed dose. So the weighted absorbed dose is equals to your absorbed dose for a defined tissue for radiation R into the weightage factor, to the radiation weighting factor, and this cumulatively will give you what we call as equivalent dose. All right. So these are the weighting factor, radiation weighting factor for different type of radiation and different energy range. For example, for photons having all energies have a radiation weighting factor of 1. Again, for electrons, muons, and of all energy, they again have radiation weighting factor of 1. For neutrons having energy less than 10 keV, they have a radiation weighting factor of 5. For neutrons having energy in the range of 10 to 100 keV, they have radiation weighting factor of 10, and so on and so forth. So radiation weighting factor, it varies with radiation type and also on the energy range. So the radiation weighting factor are needed because different types of radiation like alpha, beta, gamma and neutrons have different effect even if absorbed dose is same. So eventually if I give 1 gray to this tissue, the response won't be similar for 1 gray of alpha particles, 1 gray of beta particles, or 1 gray of photon, or 1 gray of neutron. Response is different because of the inherent way by which these radiation interact with the matter. All right. So in radiation protection, 1 sievert is a large quantity and thus expressed in the units of millisievert, microsievert. So I forgot to tell you one thing, that this equivalent dose has a unit called as sievert. So whenever we multiply our absorbed dose in gray with our radiation weighting factor, we get an equivalent dose and it has units in sievert. And in radiation protection, 1 sievert is basically a large quantity, and thus we express in the units of millisievert, microsievert and so on and so forth. Now next is effective dose. So now the question is, exposure to radiation, it may occur to whole body, which we call as uniform irradiation. So we have this human body over here, have a source over here. So exposure can happen to the whole body by means of uniform irradiation, or it can happen to a defined region through a non-uniform irradiation, or to a defined or individual organs of the body. So irradiation can be both uniform and non-uniform irradiation can be there. And non-uniform irradiation has to be restricted in order to restrict not only deterministic effect but also stochastic effect. So we'll talk more about deterministic effect and stochastic effect in the later section. But still, as of now, we'll give a brief glimpse. The deterministic effect is threshold dependent. So for that and dose response curve. So for deterministic effect, we have a defined threshold dose. Up to this dose, there will be no response. But after this threshold dose, the effect will keep on increasing. But for stochastic effect, we don't have a defined threshold dose. There is equal probability of getting a defined cancer at all doses, but the response keep on increasing as the dose keep on increasing, as the dose keep on increases. So non-uniform irradiation has to be restricted in order to restrict not only deterministic effect but also to minimize the stochastic effect. So ICRP, it recommended dose limits for stochastic and deterministic effect. So now if several tissue like T1, T2, 3, T4, so we have tissue 1, tissue 2, tissue 3, tissue N, and if these several tissues, it receives equivalent dose of HT1, HT2, HT3 and so on and so forth. So the total risks of the individual, total risks to the individual should not exceed from the resulting stipulated dose limit to uniform whole body irradiation. So after getting this amount of radiation equivalent dose to this different tissue, the total risks, because after radiation development, definitely there are some risks to this different tissue of getting some getting bygone. So definitely, but the total risks of the individual who have received this amount of equivalent dose to this tissue should not exceed from the stipulated dose limit to uniform whole body irradiation. And a number of organs are considered based on sensitivity and seriousness of damage by radiation, and risk factor are age and sex dependent. So depending on the extent to which risks from stochastic effect in a tissue or organ may contribute to the total risks from stochastic effect, a tissue weighting factor is assigned to each organ or tissue. So now the question is how we can calculate effective dose. So first is you need to calculate the absorbed dose to define organ and tissue, and you can define and you can calculate absorbed dose in the units of Gray. And after we calculate absorbed dose, we have to multiply them with the radiation weighting factor, and this will give us an effective, or it will give us an equivalent dose. And multiplying this equivalent dose with tissue weighting factor will give us what we call effective dose. So starting with radiation, starting with the calculation of absorbed dose in two organs and tissue, next is multiply the calculated values of absorbed dose by radiation weighting factor, and the result which you will be getting, it will be in Sievert, and what we call as equivalent dose and expressed in Sieverts. And sum of the equivalent doses to individual organs and tissue for organ number 1, 2, 3, 4, 5, and multiplying each of this equivalent dose by a tissue weighting factor will give us the effective dose. So effective dose is again in Sievert and is a well-known quantity that is often referred to as simply as dose. So effective dose equals to the equivalent dose times the tissue weighting factor for all the tissue to give us the effective dose and its units in Sievert. So where ST is the tissue specific equivalent dose in tissue T, and WT is our committee determined dimensionless tissue specific weighting factor. And these are the different tissue weighting factor for defined by ICRP 2007 and ICRP 1991. For breast, the tissue weighting factor is 0.12. In ICRP 1991, it was 0.05. And you can see a variety of values which is being assigned to each tissue or organ type. So highest are having bone, bone marrow, breast, colon, lung, stomach, and remainder of the remainder and corners, and are having a tissue weighting factor of 0.08 and so on and so forth. So that's the radioactive material is emitting radiation. So activity is defined as the number of disintegration happening per unit time. So activity is lambda n, or dn by dt equal to for decay is equals to minus of lambda n. And intensity of gamma rays measured in Röntgen. So amount of charge created in this air will be given by the term called as exposure by Röntgen, and how much radiation is being absorbed by the defined volume will give us the absorbed dose, and absorbed dose multiplied by the radiation weighting factor will give us our equivalent dose, and equivalent dose multiplied with the tissue weighting factor will give us effective dose. So I guess this will be clear to you as of now. So again, repeating this thing, absorbed dose multiplied by the weighing factor will give us an equivalent dose. Equivalent dose for each tissue multiplied by corresponding tissue weighting factor will give us the effective dose E. So next is on the annual limit of intake. So the annual limit of intake is the greatest value of annual intake of a specified radionuclide, which will result in a computed dose equivalent not exceeding the annual dose equivalent limit. So even if I take this, so basically the ALI is the greatest value of the annual intake of a specific radionuclide, which will not result in exceeding the critical value which is being prescribed by our competent authority. And these are the different ALI value for P32, carbon 14, tritium 3, sulfur, and these are the values in Backwheel for ingestion and inhalation. And last is on derived air concentration. So the maximum concentration of a radionuclide in the ambient air, which if inhaled by a person for 2000 hours in a year at a breathing rate of 1.2 millimeter cube per hour, will not result in annual effective dose equivalent to excess of the limit prescribed by the competent authority, and DAC equal to ALI by 2.4 cross times number 3 Becquerel per meter cube. So that's the DAC, that's the maximum concentration of a radionuclide in the ambient air. And if we inhale this air for 2000 hours in a year at a breathing rate of this one, will not result in the crossing the critical value which is being prescribed by our competent authority. So that's all for today, and if you like this video, please like, share and subscribe, and thank you so much for watching, and please give your valuable feedback in the comment section. So thank you so much.